Independent events. Examples. Suppose we have 10 keys, 2 of which will open a certain lock. We draw 2 keys at random, without replacement. Let A be the event that the first key drawn opens the lock, and B the event that the second key drawn opens the lock. The question is, are these 2 events, A and B, independent? What if the keys are drawn with replacement instead of without replacement? Well, let's start by determining the probability of the event A. A is the event that the first key drawn opens the lock. There are 2 keys which will successfully open the lock out of 10. The probability of A is therefore 2 over 10. We have the same argument on the second key. There are 2 keys which may appear on the second draw and will open the lock out of 10. The probability of the event B is also 2/10. What about the probability of A intersect B? That's the probability that both the first key drawn and the second key drawn will open the lock. There are 2 choices for the first key, which will successfully open the lock, and only 1 remaining on the second draw, so the numerator is 2 times 1. On the other hand, if we draw 2 keys out of 10 without replacement, there are 10 times 9 possible ways of doing this. So the probability is 2 times 1 over 10 times 9, or 2 over 90. This is clearly not the same as the probability of A times the probability of B. So in this case, the 2 events A and B are not independent. They are dependent events. 3-student example. Alice, Ben, and Carol write a test. Alice has a 90% chance of passing the test, Ben a 70% chance, and Carol an 80% chance of passing the test. What's the probability that Alice is the only one of the 3 to pass this test? Let's begin by defining 3 events. A is the event that Alice passes, B is the event that Ben passes, C is the event that Carol passes. And we're clearly going to assume that these 3 events are independent. There is no collaboration among these 3 people. Then the probability that Alice is the only one to pass the test is the probability of the event A and B complement and C complement, which by independence is P of A times P of B complement times P of C complement. Now P of A is 0.9, P of B complement 0.3, P of C complement 0.2. And so we multiply these 3 together to get the probability Alice is the only one to pass the test. What if we're asked for the probability that exactly one of the 3 students passes the test? Define this to be the event D. What's P of D? D can occur in 3 mutually exclusive ways. Alice can pass, Ben and Carol fail. Ben can pass, Alice and Carol fail. Or Carol can pass, and Alice and Ben fail. And so the probability is the sum of the probability of those 3 events. We've already computed the probability of the first of these, 0.9, 0.3, 0.2, and the second and third are calculated in the same fashion. And when we add these together, we end up with the probability of D somewhere around 0.092. What if we're asked for the probability of the event D2, the event that at least one of the 3 students pass the test? What's the probability of D2? This is a probability that's much easier to calculate if we go through its complement, D2 complement, because the probability of the event D2 complement is the event that no one passes the test. And that's A complement intersect B complement intersect C complement. That probability is the product of 0.1, 0.3, 0.2, 0.006. Of course, if we're interested in the probability of D2, that's 1 minus the probability of its complement, 1 minus 0.006, or 0.994. Here are 2 review questions that you can try on your own. 2 events A and B have positive probability, P of A greater than 0, P of B greater than 0, and they're independent. Is it possible that they could also be mutually exclusive? Work on this yourself, and we'll provide a solution. The definition of independence of A and B is that P of A intersect B is P of A times P of B, and since both A and B have positive probability, this product is also strictly bigger than 0. But if they're mutually exclusive, then A intersect B is the empty set, so the probability of the intersection is 0. This is not possible unless one of P of A or P of B is equal to 0. So in other words, under the condition that they both have positive probability, this is impossible. Let's now look at the solution to the second problem. The second problem said that two numbers were drawn at random without replacement from a set 1, 2, 3, 4. And we define two events. A is the event that the first number we draw is 1. B is the event that the total of the numbers drawn is 5. The question is, are the two events A and B independent? This is easily done if we simply list the events in question. For example, the sample space consists of all pairs 1, 2, 1, 3, 1, 4, 2, 1, 2, 3, 2, 4, such that the same number is not repeated twice. There are 12 elements in the sample space. Each has the same probability, 1 over 12.
The event A, the event that the first number drawn is a 1, is the event 1, 2, 1, 3, 1, 4. It has 3 elements, each of which has probability 1/12, and so the probability of the event A is 3/12. The event B, that the sum of the numbers drawn is 5, consists of the points 1, 4, 2, 3, 3, 2, and 4, 1. And the probability of B is therefore 4 over 12. The event A intersect B has 1 point, the point 1, 4 in it, and therefore has probability 1/12. Note that 1/12, the probability of A intersect B, is equal to the probability of A, or 3/12, times the probability of B, which is 4/12. And so the events A and B are independent. Although on the surface, both A and B involve the number drawn on the first draw. They seem to share information about that first number. Nevertheless, mathematically, they're independent events.